So let's go to the equations. So let's start with Reynolds stress equations. Reynolds stress equations. So the left hand side I will not focus so much now. The left hand side, some terms will drop, sometimes remains, let it be. Okay. So I am going to look at first the for I equal to 1 and k equal to 1. So I am going to substitute the value I equal to 1, k equal to 1 to get an equation for this will be u1 prime bar for this particular normal Reynolds stresses. Okay, an equation for this. So the left hand side I am not focusing so much. I would like to reveal to you what of these particular terms are there on the right hand side, right? So we are focusing on the pressure strain rate term right now. So I have 4 other terms. So symbolically one can write, before this I can write this Reynolds stress equation here. So symbolically one can write Reynolds stress equation as if you are familiar with this substantial or material derivative form, right? One can write like this, right? ui prime uk prime by dt. You are familiar with this, I think, all of you. Okay, symbolically. Then we had the dik term, dik, not the j is the divergence term, dik is the diffusion rate. I am using here diffusion rate, plus we had production rate, right, or the pressure strain rate term. Let me call it phi, yeah, I will use phi ik, sorry, and then I will use the production ik minus epsilon ik. So names are, this is your diffusion rate, sorry, this is the diffusion rate term, the pressure strain rate term, the production rate, and the dissipation rate. You will see in many textbooks and reference notes as symbolically written like this without giving out all these terms, but you already know what each of these terms looks like. Okay. So now with this I am going to take equation for u1 prime bar. So I would get the first, it will be d u1 prime by dt, that is the left hand side part. Okay, this is the LHS. So I am not worried about this. I am not worried about the diffusion rate also, because I will tell you why I call diffusion rate later. We are only focusing on this particular term here now, pressure strain rate. Okay. So this will be d11 plus I have this phi 11. So let us write it out what it will be. So it will be p prime by rho, it was dou ui prime by dou k plus dou uk prime by dou I, right. So I equal to 1, k equal to 1 will be dou u1 prime by dou x1 plus dou u1 prime by dou x1. This was the phi 11 term. So now I have the production rate term. This I would like to expand. So production rate term was, we had this minus ui prime uk prime, right. Okay. So I have this minus of, I can write minus of the production rate, which was u1 prime uj prime, right, u1 prime uj prime dou u1 bar by dou xj plus again I equal to 1, it is u1 prime uj prime, k is also 1, dou u1 bar by dou xj. So I basically get minus 2 of this. I am only expanding from the previous equation, setting I equal to 1, k equal to 1. So the production rate term looks like this, and I have the dissipation rate term. Dissipation rate is minus epsilon ik, which is 2 nu dou u1 prime by dou xj, dou u1 prime by dou xj. Okay, so this is the equation for your u1 prime bar Reynolds stresses. Diffusion rate I did not expand. One can expand it and see, not a problem. So now here the important to see here is that this will be of course 2 times s. So if I take this as LHS equal to d11 plus 2 p prime by rho dou u1 prime by dou x1 average. Okay, so this will be minus 2 of this, minus 2 of, it's the same term, minus 2 of this. So let me expand. So you will get 3 different terms. J is repeated index, so I need to sum it up. Okay, Einstein summation. So I will get u1 prime, j equal to 1 now, dou u1 bar by dou x1 plus j equal to 2 now. So it's u1 prime, u2 prime, dou u1 bar by dou x2 plus j equal to 3, which is u1 prime, u3 prime, dou u1 bar by dou x3. Okay, minus 2 nu, this you see is the same term, so it is squared. So this is dou u1 prime by dou xj square, dou xj, it will be squared here, right? So this is square term, so it will become dou xj. Okay, it's straight away to see here that this last term must be greater than or equal to 0, and there is a negative sign. Okay, and at least it is revealing, giving a clue why we are calling this a destruction rate, because it is minus of a positive value. It is taking away something from the system. Okay, I will come to that later. So I have this term. So now we apply what we learnt about this plane Couette flow when it has reached statistical stationarity and it has exhibiting homogeneous in the 2 direction. So any terms which will go away in the terms that we have here. What about the first term here? Oh, before that, does this term goes away or that it remains? Somebody said 0. Why it is 0? Fluctuation mean. Do you have pressure fluctuation also? Is it 0? This is not 0. It's a correlation of pressure fluctuation and strain rate fluctuation. So that's why the name came pressure strain rate. This is not 0, it's a correlation term. And we cannot apply any other rules here, the statistically homogeneous thing, because that is not for, that is for a gradient of a statistical term, anything in this over bar, and there is no gradient that we are looking into, right? But what about this particular term here? Dou by dou x1 of any statistical quantity, right? So this is 0, homogeneous along x1, right? Statistical homogeneity along x1 for the plane Couette flow. Okay, so we are obviously looking into only plane Couette flow, as I already said. Plane Couette flow is what we are discussing, applying the equation for that particular flow. What about the second one? This is non-zero because this is the main gradient term that you have, mean strain gradient. X2 is the wall normal direction, right? So this term remains. What about the third term? 0, dou by dou x3, right? So this is 0. Same thing here, statistical homogeneity along x3 as we discussed. So this particular P11, so what is this? This is P11 term. P11 is non-zero here. Okay, so there is a production rate term existing for your one of the Reynolds stress term. Okay, so that is fine, and this is also surviving here. This term is a correlation we need to retain. So now let's see what will happen to the equation for I equal to 2, k equal to 2. Okay, so I equal to 2, k equal to 2, which will give you u2 prime over bar. So the LHS will be du2 prime by dt equal to d22 plus I have the pressure strain rate term, which is P prime by rho. This is I and k, I equal to k here, so it's dou u2 prime by, or I can simply write, since you are already experts of all this, it's easy to see that it will become dou u2 prime by dou x2, right, minus this will also have 2 of this because it's I k, I prime k prime, I prime ui prime uk prime, and then you will also get uk prime uj prime and ui prime uj prime. So I equal to k will give you u2 prime uj prime. So I get minus 2 for this, I get u2 prime uj prime, and then I get dou u2 bar by dou xj, minus 2 of this. Okay, that's correct. Yes. So I would get this as the production rate term, minus 2 nu, again it's ik, so that means it will be u2 prime by dou xj. So this is the epsilon 22 term here. Okay, if I write it out, this will be the epsilon 22. This is my P22 term. This is the phi 22. So now let's expand the production rate. This plus this. We cannot say anything about the phi 22, the pressure strain rate, because it's a correlation. Let it be as it is. Only the production rate we are focusing. So minus 2 of, again u2 prime u1 prime dou u2 bar by dou x1 plus j is now 2, repeated index you have to sum it over, so it becomes u2 prime dou u2 bar by dou x2 plus u2 prime u3 prime dou u2 bar by dou x3 minus of your epsilon 33. Okay. So now we again see the production rate term P22, what will happen to that? So you see dou by dou x1 homogeneous, this term is gone. It's also u2 bar is 0 here. Okay, that is also there. u2 bar itself is 0 when the flow is fully developed, correct. So this entire term will go away, both because of u2 bar is going away. So there is no gradient for u2 bar because fully developed. u2 bar is 0 here for a plane coed flow. Also the first and last one is also because of the homogeneity, also you can also say dou by dou x1, dou by dou x3 of that. So what did this happen? So now what is happening here is that your P22 is 0. Okay, poor fellow, this particular Reynolds stresses has no production rate. P22 is 0 for it. And epsilon 33, there is a sink term, this is a square. So the dissipation rate is occurring here. Okay, nobody is to produce any turbulence for it, but there is somebody destructing whatever is left. Okay, so we will see what happens to this particular term. Right now we don't know what these stresses look like for this. We don't have we have not applied any data. We have only considered a flow problem and then applying conditions. Okay, so P22 is 0, and we will see next what happens to the next, which is I equal to 3, K equal to 3, which is U3 prime average. I get d U3 prime by dt equal to d33, the diffusion rate, plus the phi 33, which is 2 p prime by rho dou U3 prime by dou x3 average, minus 2 of, I have now U3 prime Uj prime dou U3 bar by dou xj, minus 2 nu dou U3 prime, okay, dou U3 prime by dou xj squared average. This is your epsilon 33. Again, there is a destruction rate here, and we also have the pressure strain rate term available, but U3 bar is 0. I don't have to expand here. U3 bar is 0 for a fully developed, again, fully developed turbulent plane co-ed flow. U3 bar is 0. Not, yeah, yes. No, that's what I said. So I will show you the data. This data that U2 bar and U3 bar are 0, I will show later. From the data I know that these two velocities are 0. We can only say that the flow is homogeneous along the x1 and x3. That is also from the data. We can see that. That is no problem. You can go ahead and do it. All I am trying to do now is to tell you what is the role of pressure strain rate. Right? I called it redistribution. I want to prove it to you that it is redistributing. For that I am taking help of a particular flow problem, and I have the direct numerical simulation data done by myself. So I am going to show you those data to prove what it does. In a given problem, you can go ahead and see what it does. It does what it does, what we are going to reveal to you. Okay. So here what happened now, P33 is 0 again. So no production rate term also for this, and dissipation rate is working very hard. It is removing the turbulence from the system. Okay. So, and then we will see the data of these three terms to see what exactly happens to these three terms. Okay. So I can show you one graph. So I am showing you the RMS data. I will come to that detailed discussion in the next class of this flow problem, but just to give you a clue. So I have plotted the RMS data taken from my own direct numerical simulation, right. So this is instead of this, let us say this is the your wall normal coordinate x2, okay, and I have the three RMS component here, u, v, w, which is basically your u1 RMS. This v RMS is the wall normal, that is our u2 RMS. This is the u3 RMS, or the stresses, or you can think this of as, you already know RMS means if I square this I will get the stress, right. Upon squaring I would get this one, this. Is this 0? all the terms. Who is producing then? U1 prime, obviously there is a production rate. That term is working very hard. The production P11, the most hard working. Okay.